Hello everyone, welcome to the second lecture of this fifth module of the course finite element method. So in the earlier lecture we have discussed the concept of this isoparametric element, and there we have seen how in case of the curved surfaces or irregular geometries the isoparametric elements are used efficiently. And there we have discussed different formula and some derivations regarding the natural coordinates in case of the one dimension and two dimensional elements. And the natural coordinator epsilon, its formula we have seen, and based on the different formula in case of the one dimension and two dimensional natural coordinates we have solved two different numericals. Okay, so these are the things that we have discussed in the last lecture. Now in this lecture we will discuss the topic which is the isoparametric, subparametric and superparametric elements, and regarding this topic we will also discuss some derivation, and based on those different formula of the derivations we will discuss some numericals in this lecture. So let us start this lecture. Again, these are the course objective and course outcome for this sub course or the subject finite element method, and it is the COPO mapping. So we will start from this slide here, the isoparametric elements for two-dimensional problems. So, three different terminology like isoparametric, superparametric and subparametric elements we will discuss first. So in the last lecture we have discussed the concept of these isoparametric elements, and there we have seen that the triangular or rectangular elements, these are not actually very useful or efficient in case of the irregular geometries when we perform the discretization, but in those cases, that is in case of the complex geometries or irregular geometries or the curved surfaces, then to perform the discretization such isoparametric elements are used. And the for the triangular or rectangular element, what is the shape of the parent element and what is the shape of the isoparametric element, that thing we have discussed in the last lecture. So here in this figure 5.12 we can see one isoparametric element, and the shape functions are used for defining the geometry and displacements of the element. Now in this isoparametric element, which you can see in the figure 5.12, the nodes used for defining geometry, that is represented with a dot sign, black dot, and the triangular sign or the notation, these are used for defining displacements. Now in this element all the 8 nodes are used in defining geometry as well as the displacements. Now if the number of nodes used for defining the geometry is same as the number of nodes used for defining the displacements, then it is known as the isoparametric element. So again, this is the concept of this isoparametric element. That is, if the number of nodes used for defining the geometry it is same for the number of nodes used for defining the displacements, then it is known as isoparametric elements. Next we are having the superparametric element. Let us consider the element which is given in the figure 5.13. Here also the black dots, these are nodes used for defining geometry, and the triangular nodes, these are used for the defining displacements. Now in this case and or in this element 8 nodes are used to define the geometry, and 4 nodes are used to define the displacements. So that means if the number of nodes used for defining the geometry is more than the number of nodes used for defining the displacements, then it is known as superparametric elements. So what we have seen in case of isoparametric element, the number of nodes used for defining the geometry, it was equal to the number of nodes used for defining the displacements. But in case of the superparametric elements, the number of nodes used for defining the geometry, it is more or higher than the number of nodes used for defining the displacements. So this is the concept of this superparametric element. Next, in case of the subparametric elements, here again we have considered in figure 5.14 one element and the black dots, these are the nodes used for defining the geometry, and triangles, these are the nodes used for defining the displacements. Now in these elements 4 nodes are used to define the geometry and 8 nodes are used to define the displacements. So that means what if the number of nodes used for defining the geometry is less than the number of nodes used for defining the displacements, then it is known as the subparametric element. So these are the difference in between the isoparametric, superparametric and subparametric element. Now let us discuss the one-dimensional shape function for isoparametric formulation of the bar element. Now earlier in case of the one-dimensional and two-dimensional problems, we have discussed the concept of the shape function, and there we have seen the different formula regarding the shape function n1 and n2, and based on this different formula we have discussed a number of numericals in the earlier modules. Now in case of this isoparametric element, again we will derive this one-dimensional shape function of the bar element. Now let us consider a bar element with nodes 1 and 2, which we can see in this diagram 5.15. Here corresponding to node 1 and node 2, u1 and u2 are the displacements which are considered. So u1 and u2, these are considered as degrees of freedom of this bar element. Now first, the natural coordinate epsilon is attached to the element with the origin located at the center of element. So which you can see here in figure 5.16, the natural coordinate epsilon, this is attached here. Corresponding to node 1 we are having epsilon is -1, and corresponding to node 2 we are having epsilon is 1. The epsilon axis need not to be parallel to the x-axis, this is only for the convenience. Now we'll consider the bar element to have 2 degrees of freedom, axial displacements u1 and u2. These are at each node associated with the global axis. So these two displacements u1 and u2 corresponding to the nodes 1 and 2, these are the 2 degrees of freedom and the axial displacements for this considered bar element. Now when the natural coordinate epsilon and x-axis are parallel to each other, then epsilon and x coordinates can be related by using this formula, that is x equals to xc plus L by 2 into epsilon, which is equation number 5.15. And here xc, it is the global coordinate of the element centroid. Now using the global coordinates x1 and x2, we can write xc, this is equals to x1 plus x2 by 2. So this is our equation number 5.16. Now if we substitute this value of xc in the equation 5.15, then we can write x equals to x1 plus x2 by 2 plus L by 2 into epsilon. Again, you know that L1 this is equals to x2 minus x1. And this concept we have applied in the earlier lecture while considering the natural coordinates of 1 and 2 dimension. So if we apply this L equals to x2 minus x1 in this equation number 5.15, then after several steps we are getting this x2 minus x1 by 2 into epsilon. This is equals to x minus x1 plus x2 by 2. So finally we can express the natural coordinate epsilon in terms of the global coordinates as epsilon this is equals to x minus x1 plus x2 by 2 multiplied by 2 by x2 minus x1. It is equation number 5.17. Now here this bar element, it has got 2 degrees of freedom, so it will have 2 generalized coordinates. So that means x equals to a1 plus a2 into epsilon, which is our equation number 5.18. Now here the limit of the epsilon, it is such that minus 1 less than equal to epsilon less than equal to 1. So epsilon lies in between minus 1 to 1. Now solving this a1 in terms of x1 and x2, we can get x equals to half multiplied by 1 minus epsilon into x1 plus 1 plus epsilon into x2, which is our equation number 5.19. So after several steps we will get this one. Now if we represent this equation number 5.19 in matrix form, then we are getting that the x matrix is equals to half, then within a row matrix of 1 minus epsilon multiplied by 1 plus epsilon multiplied by a column matrix x1 x2. Now instead of this half multiplied by the row matrix, instead of this part we can write a row matrix of n1 n2. Now the displacement function x, this is equals to n1 u1 plus n2 u2. So here the shape function n1 this is equals to 1 minus epsilon by 2 and n2 this is equals to 1 plus epsilon by 2. So this is the formula for the shape function here. N1 equals to 1 minus epsilon by 2 and n2 equals to 1 plus epsilon by 2. And here n1 and n2 they obey that definition of the shape function, that is the shape function will have a value equal to unity at the node to which it belongs and 0 value at the other nodes. Now in this figure 5.17 we can see the shape function variation with natural coordinates. In figure 5.17a, in case of the shape function n1, you can see that the value of this n1 is having a value equal to unity at the node and 0 at the other nodes. In this similar manner, we can see that in case of figure 5.17b, the value of n2 it is having a value of unity at its corresponding node, that means to which it belongs, and 0 value at the other nodes. And the linear displacement field, that means for this bar element corresponding to node 1 and node 2, we can see that epsilon is -1 at node 1 where the displacement is u1, and epsilon is 1 at node 2 where the displacement is u2. So these are the formula for the shape function corresponding to a bar element in case of this isoparametric formulation. Next we will discuss the shape function for 4-noded rectangular parent element by using natural coordinate system and coordinate transformation for 2-dimensional. So in this diagram you can see the 4-noded rectangular parent element. It is shown here. And the coordinates for the 4 nodes of this rectangular element, these are also shown. So this is the 4-noded rectangular element. We have considered the parent element is defined in epsilon and eta coordinates, that is natural coordinates. Now epsilon is varying from -1 to 1 and eta is also varying from -1 to 1. Now from our concept of the shape function, we know that shape function value, it is unity at its own node and its value is 0 at the other nodes. So that means what? At node 1 the coordinates epsilon, this is equals to -1 and eta is equals to -1, which you can see here in this figure 5.18. At node 1 the coordinate is -1 -1, so that means epsilon is -1 and eta is also -1. The shape function n1, this is equals to 1 at node 1 and n1 is 0 at nodes 2, 3 and 4, because this shape function n1, it belongs to the point or the node 1, so there its value will be 1 and for the other nodes its value will be 0. So n1 has to be in the form of n1 equals to c into 1 minus epsilon into 1 minus eta, that c is constant, and this is our equation number 5.20. Now if we substitute the value of epsilon and eta as -1 in this equation 5.2, then we are getting the value of n1, this is equals to 4c. Now at node 1 the value of n1 is 1, so that means the value of the constant c, this is equals to 1 by 4. Now if we put the value of this c as 1 by 4 in equation number 5.20, then we are getting the value of n1, this is 1 by 4 multiplied by 1 minus epsilon multiplied by 1 minus eta, so this is our equation number 5.21. So in this similar manner we can calculate the value of n2 at node 2. So for that, at node 2 the coordinates are epsilon is 1 and eta is -1, which we can see here in this diagram. The coordinate is given for node 2, it is 1 -1, so that means epsilon is 1 and eta is -1 at node 2. Now from the characteristics of the shape function, we know that the value of node 2 is 1, that means the value of n2, it is 1 at node 2, because this n2 it belongs to node 2, but it is 0 for the node 1, 3 and 4, because this n2 it does not belong to the other nodes. Now here also the mathematical representation of this node 2, that shape function, it is C into 1 plus epsilon into 1 minus eta. Now if we substitute the value of epsilon and eta as 1 and minus 1 respectively, then we are getting the value of C as 1 by 4 after 3 steps. So that means finally we are getting the value of n2, this is equals to 1 by 4 multiplied by 1 plus epsilon into 1 minus eta. So this is our equation number 5.23. Next, in this similar manner, we can calculate the value of the shape function at node 3. So the coordinate for the node 3, it is given 1 1, so that means epsilon is 1 and eta is also 1. Again the shape function n3 at node 3, this is 1, and the value of n3 is 0 at node 1, 2 and 4. Now the n3's mathematical representation, it is C into 1 plus epsilon into 1 plus eta. So now if we put the value of epsilon and eta in the mathematical representation of n3 in equation number 5.24, then after several steps we are getting the value of C equals to 1 by 4. So again the value of n3 we are getting as 1 by 4, 1 plus epsilon into 1 plus eta as equation number 5.25. So in the similar manner again we can calculate the value of node 4. It is the value of the shape function n4 at node 4 we can calculate. So at node 4, from the given diagram you can write the coordinate epsilon is -1 and eta is 1. So that means the shape function n4 it is 1 at node 4 and the value of n4 it is 0 at node 1, 2 and 3. So the mathematical representation of n4 it is C into 1 minus epsilon into 1 plus eta. Now if we substitute epsilon is -1 and eta is 1 in equation number 5.26, then we are getting C equals to 1 by 4 after 3 steps. So that means the value of n4 we are getting as 1 by 4 into 1 minus epsilon into 1 plus eta. So this is our equation number 5.27. So in this way we have calculated the value of the shape functions n1, n2, n3 and n4 at 4 different nodes. Now if you consider a point P with coordinate epsilon eta. Now if displacement function u equals to a column matrix of ub represents the displacement components of a point located at epsilon eta coordinate, then we can write u equals to n1 u1 plus n2 u2 plus n3 u3 plus n4 u4, and v equals to n1 v1 plus n2 v2 plus n3 v3 plus n4 v4. Now in matrix form it can be represented like this, equation number 5.28. So u equals to a column matrix of ub, which is the multiplication of two different matrices. Now in this isoparametric formulation, that is for global system, the coordinates of the nodal points are x1 y1 x2 y2 x3 y3 and x4 y4. Now to get mapping, the coordinate of the point P is defined as x equals to n1 x1 plus n2 x2 plus n3 x3 plus n4 x4, and y equals to n1 y1 plus n2 y2 plus n3 y3 plus n4 y4. In case of figure 5.19, we can see that the four-noded quadrilateral element or the mapped element, the point P is there inside this mapped element. Now these coordinates of the P, it can be also represented in the matrix form, which is our equation number 5.29. Let us next discuss the element stiffness matrix equation for 4-noded isoparametric quadrilateral element. Now the parent element and the isoparametric quadrilateral element, these are given here. Now assembling the element stiffness matrix for the isoparametric element, it is very tedious process since it involves coordinate transformation from natural coordinate system to global coordinate system. Now these two displacement function u for the parent element and for isoparametric quadrilateral element we have discussed just now. So this representation we have seen. So the Jacobian matrix J equals to a 2 by 2 matrix. This is J11, J12, J21, J22. Now here the formula of the J11, J12, J21, J22, these are given here. This formula we need to remember to solve the numericals to calculate the Jacobian matrix for this isoparametric element. Now since the strain E, this is equals to 1 by J determinant multiplied by a 3 by 4 matrix multiplied by one more matrix, then one column matrix. This is our 5.60. This is the mathematical representation of the strain matrix, so which is a very complicated one, and we need to have a lot of practice to remember this one. This is equation number 5.60. Now the general mathematical representation of the strain E, this is equals to B into U. This is known to us. So that means finally we are getting the equation of this B matrix, which is a strain displacement relationship matrix. It is represented as equation number 5.63. So this is the strain displacement relationship matrix equation for the isoparametric quadrilateral element. Now for natural coordinates, we are getting this equation number 5.64, that is for the K matrix. Now in this K matrix representation, T is the thickness of the element, J is the determinant of the Jacobian, epsilon and eta, these are the natural coordinates, B is the strain displacement relationship matrix, and D is the stress strain relationship matrix. So some more complicated mathematical representation or mathematical formula we are getting here in case of these isoparametric elements. So some of this formula we need to remember to solve the numericals based on this concept. Now for the two-dimensional problems, the stress strain relationship matrix D, it is given here, and here the E is the Young's modulus and U is the Poisson's ratio. Now there is one more formula in case of the element force vector, which is Fe. This is equals to nt multiplied by column matrix of fx fy, where n is the shape function, fx is the load or force on x direction, and fy is a force on y direction. Let us discuss one numerical based on this concept. We need to evaluate the Cartesian coordinate of the point P, which has local coordinates epsilon is 0.6 and eta is 0.8, which is given here in the diagram. Now the natural coordinates of the point P, epsilon is 0.6 and eta is 0.8. Now the Cartesian coordinates of the point 1, 2, 3, 4, these are given here, so we can write the value of x1, x2, x3, x4 and y1, y2, y3, y4 for the 4 different nodes. So we need to find the Cartesian coordinates of the point P. So First we will start from the shape function equation, and the formula for the shape function we have derived earlier. So the formula for this n1, n2, n3 and n4 we need to remember, and we have applied here. So for all the cases, to find the value of the shape function, we need to put the value of epsilon and eta. These are given in this numerical. So we can find the value of the 4 different shape function. Now we need to put these shape function values in the formula of the Cartesian coordinate x and y. So the formula of coordinate x, it is n1 x1 plus n2 x2 plus n3 x3 plus n4 x4. So all the values of these shape functions and x1, x2, x3 and x4, these are known to us, so we can finally calculate the x coordinate is 5.82, and in this similar manner we can calculate the y coordinate is 7.02. So finally we are getting the Cartesian coordinate of the point P. This is 5.82, 7.02. So these are the concept of these isoparametric, superparametric and subparametric element. And regarding these isoparametric elements, we have seen the shape function formula, then stress strain relationship matrix, Jacobian matrix, the formula for all these different terminology, and based on this concept and the formula we have discussed one numerical in this lecture. In the next lecture we will discuss some numerical problems based on the isoparametric elements. So this is the end for this lecture.